Hello. This lecture is a brief overview of the important concepts from linear algebra that we will use throughout the course.
Let me begin by recalling the notion of a vector space. Let F be the finite field on Q elements. Vn of F, also denoted Fn, is the n-fold Cartesian product of F with itself. This is a set of all n tuples whose components are elements of the field F. So Vn of F is an n-dimensional vector space over F, where vector addition is component-wise and scalar multiplication, which is the multiplication of a field element with a vector, is also component-wise. Now, subset C of Vn of F is a vector subspace of Vn of F if C is non-empty, closed under addition, which means that for all vectors x and y in C, their sum is also in C, and closed under scalar multiplication, which means that for all vectors x in C and all scalars lambda in F, the scalar product of lambda and x is also in C. I'll note that a vector subspace of Vn of F is also a vector space over F. The elements of a vector space can be described in terms of a basis for that vector space. To define a basis, I'll need the notion of linear independence. So let C be a vector space over F, and let V1 through Vk be vectors in C. A linear combination of these vectors is a vector in C of the form lambda 1 v1 plus lambda 2 v2 plus lambda k vk, where the lambda i's are scalars in the field F. The span of vectors v1 through vk, denoted like this, is a set of all linear combinations of v1 through vk. Note that the span is a vector subspace of the vector space C. Now, vectors v1 through vk are said to be linearly independent over F if the only linear combination of these vectors that gives a zero vector is a trivial linear combination where all the scalars are zero. If there is a non-trivial linear combination of these vectors that gives you the zero vector, then the vectors are said to be linearly dependent over F. Now, if these k vectors are linearly independent over F, then each of these linear combinations gives a unique vector v in the vector space. Since there are q choices for each scalar, and k scalars in total, the size of the span of v1 through vk is q to the power k. Otherwise, if these vectors are linearly dependent over F, then their span has size less than q to the k. A basis of a vector space C over F is a linearly independent set of vectors which span the vector space. So a basis is a linearly independent spanning set. Here are some basic facts about bases. Every vector space has a basis. In fact, C can have many bases. All bases of C have the same size, which is called the dimension of the vector space. If C has dimension k, then the size of the vector space is q to the k. I'll remark that the set C, consisting of just the zero vector, is a zero-dimensional vector space over F. My convention is that its basis is the empty set. I'll next review some basic properties of matrices. So, of course, matrices can be added and subtracted as long as they have the same dimensions. So let A and B be two m by n matrices whose entries lie in a field F. Then A and B are added component-wise and also subtracted component-wise. We can also multiply matrices. So if A is an m1 by n1 matrix over F, and B is an M2 times N2 matrix over F, then the product of A and B is only defined if N1 equals M2. So the number of columns of the first matrix must equal the number of rows in the second matrix. If this is the case, then the product of A and B has dimensions M1 by N2. The ijth entry of the product is obtained by taking the inner product of the ith row of A and the jth column of B. Let C be a vector space over F with basis V1 through Vk. Then C can be described by the K by N matrix whose rows are the vectors in the basis. Note that G has K rows and N columns, so it's a K by N matrix. Since every element in C can be described uniquely as a linear combination of the basis vectors, we can view C as being the product of all vectors of length K over F times a matrix G. This is because when you multiply such a vector with the matrix on the right, then the elements of the vector multiply the corresponding rows of the matrix. And so this product is M1v1 plus M2v2 plus MKvk. Hence, C is precisely the row space of G, which I'll define on the next slide. Let A be an M by N matrix over a field F. The row space of A is the vector subspace of Vn of F, spanned by the rows of A. The row rank of A is the dimension of its row space. The column space of A is the vector subspace of Vm of F, spanned by the columns of A. The column rank of A is the dimension of its column space. A fundamental fact is that the row rank and column rank of a matrix are equal to each other, and that's called the rank of the matrix. Here's an example. Let's determine the dimension of the vector space C of V5 of Z5 that is spanned by these vectors V1, V2, V3, and V4. Note that these vectors are over Z5, so their components are integers modulo 5. We can answer this question by writing down a matrix G, whose rows are the vectors V1, V2, V3, and V4. So G is a 4 by 5 matrix. Then the row space of G is precisely the subspace C. And so the row rank of G, which is also its rank, will be the dimension of C. So we'll use elementary row operations to determine a reduced row echelon form of the matrix G. I'll begin by making this leading entry 1 by multiplying the first row of G by 2. I chose 2 because 3 times 2 is 6, which is congruent to 1 modulo 5. And so the inverse of 3 in the integers modulo 5 is 2. So multiplying the first row of G by 2 gives this new first row. Next, I'll zero out these entries below the first leading 1 by subtracting twice row 1 from row 2, which will make this entry 0, and subtracting twice row 1 from row 4, which will make this entry 0. I get this matrix, whose first column is now a leading column. Next, I'll zero out this entry by subtracting 4 times row 2 from row 3. And I'll zero out this entry by replacing row 4 by row 4 minus row 2. So I get this matrix, which now has 2 leading 1s. And finally, I'll replace row 4 by row 4 minus row 3, which zeroes out the last row. The reduced matrix has 3 leading non-zero entries, and its last row is 0. So the matrix has rank 3, and hence the row space of G has dimension 3. So we conclude that the dimension of the vector space spanned by the 4 vectors is 3. Here is my last set of definitions. Let A be an n by n matrix over a field F. The null space of A is a set of all vectors x, such that A times x transpose equals 0. You can prove that the null space of A is a vector subspace of Vn of F. Its dimension is called the nullity of A. A fundamental fact is that the rank of a matrix plus its nullity equals the number of columns in the matrix. Now let's consider square n by n matrices. Such a matrix A is said to be invertible or non-singular if there exists an n by n matrix B such that A times B equals B times A equals the n by n identity matrix. If A is invertible, then the matrix B is called the inverse of A. A basic fact is that A is invertible if and only if it has rank n, which is equivalent to saying that it has non-zero determinant.